All right, let's get started. Last time we talked about what? Was value iteration, right? Like we started to talk about value iteration. Can someone quickly tell me what value iteration does in your own words? What is it trying to compute first? Okay, yeah. An optimal policy, okay. All right, yeah, maybe. How does it do it? Oh, isn't that policy iteration? Okay, yeah. Policy iteration is going to be covered today. And that I would describe the way you described this algorithm. You have a policy, you evaluate it, and then try to make it better. But okay, so go back to value iteration. Like, what is that? What's it trying to do? Yeah.
State values given policy more of a expected sum of the word.
Something like that, yeah. I mean, improves, yeah, state values. So there is a value function that we are refining. We are refining some function that assigns values to states in an iterative fashion. And what is the purpose? Like, where do we want to get with this?
Try to find the true value function.
Okay, given a policy?
Oh, given the state. Yeah.
The value function already, assigns values to every state. Yes? Correct. We are trying to find the value function underlying the optimal policy or the optimal values. I guess you all know this, but so that's what it's trying to do. How is it trying to achieve this? What's the basic technique? Okay, so there is something called the Bellman maybe optimality equation. What does it do with that? What's the Bellman optimality equation? What does it have to do with value iteration? The Bellman optimality equation. Maybe the Bellman optimality operator that we were talking about. That does that, right? But there is a connection to the Bellman optimality equation, correct? What is it? Yes.
So it's going to take the old value, put it in the Bellman optimality equation, and keep iterating over that until it's stable. Value
Correct. The only small thing I would add to that is that, of course, this equation has two sides. And you're talking about the right-hand side, which was the complicated side with the rewards, the transitions, and so on and so forth. It's kind of like using the Bellman optimality equation to refine value estimates in an iterative fashion and recomputes these values. It repeats it a number of times until the values do not change much. Then what do we do with that? So, okay, fine, we stop. The values do not seem to change. What do we do? Yes? Okay, how do we do that? Huh? No, we don't need policy iteration for that. Something simple. That's right. Like you do as if you were computing the next iterate, but instead of actually computing it, you just look at what are the maximizing actions in this Bowman optimality equation, and remember those. For every state, we're going to remember what action was the maximizing action. That gives us a policy, which we call, was the special word that we used for talking about policies of this form, which are maximizing something. It's a greedy policy, and it's greedy with respect to the value function estimate that we just produced. Okay. Okay, that's the plan. And so the last time we talked about, and we got to the point where we could argue that this process leads to value function estimates which are getting closer to the optimal value function, right? So in value iteration, you're calculating these value estimates or like values, and they, as a function, are getting closer and closer to the optimal value function, the value function of an optimal policy. But we don't know that if we stop this process and we read out this greedy policy with respect to the last estimate, whether this policy is going to be any good. We don't know yet whether that's going to happen. The picture I have for value iteration in my head is something like this. So you have the set of possible value functions over the set of states S. V star lives somewhere in this space. This is the target. This is the optimal value function where we want the process to converge to. And we have this iterative method that starts at V naught. It makes the step, is the Bowman optimality operator, gets the next value function there, and then makes another step. This T gets another one. And it repeats. Eventually, it gets two guys, Vn and Vn plus 1, which are somehow very close to each other. And we are kind of happy, and we want to stop. And at that time, maybe we take, well, I don't know, the greedy with respect to Vn. At the same, yeah, like when you're kind of like mimicking that, oh, I would want to compute Vn plus 1. You could take the greedy with respect to Vn plus 1, but that would be further computation. We already kind of computed that policy. We just keep that policy. So that goes to the space of deterministic memoryless policies, which is the space of maps from states to actions. So this is just in this set. So this is the map that takes a function from here, and then it gives you a policy, pi, which is greedy with respect to that function. This map is such that the action chosen by the policy pi, which we compute, is the maximizing action for the right-hand side of the Bowman optimality equation, which just looks like this. And OK, I'm using VNS or VN at the moment. OK. So this is this greedy map. Sometimes I'm just going to say that pi is one of the, so gamma is going to take a function here, and it returns a set, gamma of Vn, which is the set of policies which are greedy with respect to that function. we could have ties. So this is not unique, right? Like the greedy policy is not uniquely determined, because there could be multiple maximizing actions at a given state. And if there are multiple maximizing actions, which one are we going to choose? We could choose any of them. So this map that I'm defining gives you all these policies. So it gives you a set. And so we just write that pi is in this set of greedy policies. So gamma applied to Vn gives you all greedy policies, and pi is just one of them. Okay? And we want, ideally, we want to see that this pi, this policy, no matter how we choose it from this set, is a good policy. What does it mean that it's a good policy? It means that it's going to produce high values at every state. Okay? So the value function of this policy, v pi, is naturally not larger, but possibly smaller than the optimal value function. Maybe it's not an optimal policy, right? V star is the best possible value that you could get. So if you take any other policy, you get values which are not as large as V star. And so the gap between these two is like how suboptimal V pi is. And we want, pi, the policy is. We want this policy not to be too suboptimal. So if I subtracting from V star, V pi, I get these non-negative values. And we want all these non-negative values to be small. The same thing to say is that the worst possible deviation over all possible states between Vs star, V star of S minus V pi of S, these gaps should be small. But notice that this is nothing but the maximum norm between V star and V pi, right? So what's the difference between a maximum norm and what I wrote here? The difference is that you would need to put an absolute value here. There is no absolute value here, but we already discussed that V star is always giving you larger values than V pi. So these are non-negative. So the absolute value doesn't do anything to them. So therefore, this equality holds. So we can just focus on how far the value function of policy pi is from the optimal value function in maximum norm. Anyways, that would be an upper bound on the suboptimality of policy pi. So we want this to be small. Is it going to be small? So let me draw the figure back. So there is policy evaluation. So if you take any policy pi, there is an arrow that goes back to the other space, to the space of value functions, which is evaluating the policy. That gives you function here, a point there, v of pi. And we want to conclude that if this distance is small, okay, clashes, then it's here. Then this other distance should also be small. Oh, no. This blue is not working. So this is V pi. Okay. All right, so how do we do this? We're going to prove a result that does exactly this. It says the following: let V be a function that assigns reals to all the states. It's arbitrary. Let policy pi be greedy with respect to V. In our case, V is going to be Vn. And we want to say that that the distance between V pi and V star cannot be larger than something that I don't know what it is, some constant times V, the distance between V and V star. So if V gets closer to V star, then that also squeezes the value of the policy that is greedy with respect to V to be closer to V star. So eventually, if you're pushing V to be very close to V star, you can make sure that the policy that you are reading out is near optimal. Almost optimal. All right, how do we prove this? And we will figure out this constant during the proof. So many times, well, this proof should work by just stating what we have. So one of the things that we have, one condition that we have here, is that pi is greedy with respect to V. So with our operator notation, where T was just, like this maximum part of this, of here, this was T applied to Vn and evaluated it as. So greediness, so pi is greedy with respect to V, is the same thing as saying that the policy evaluator operator applied to V gives you the same result as if you're applying the Bellman optimality operator to V. So this is what we know. We also know that V pi is a fixed point of T pi. And T pi is a gamma contraction, T is a gamma contraction. So we want to use these things. And we also know that V star is a fixed point of T. So we need to bound this. So let's start just playing around. The first thing we can do is that we can use this, the fixed point properties of V pi and V star to write that V pi minus V star is equal to T pi applied to V pi minus T applied to V star. And then we're going to subtract T pi applied to V and add back T pi to apply to V. Okay. We didn't change anything. We just subtracted and added. Question?
How do we comfortably say, like, how do we assume that T is linear? Do we know that it's linear?
We didn't use that T is linear.
Oh, wait, no, I just misunderstood. My bad. Yeah.
But why did you assume that T? Like,
no, I thought the T pi minus T pi V pi minus.
we are going to do something with that. No.
Yeah,
No, we were just subtracting this value and adding this value.
Yeah,
Right.
I misunderstood.
Yeah, that's fine. No worries. Okay. So we're just subtracting something, adding back the same thing. That doesn't change anything. And now notice that we have this property, which is just that pi is greedy with respect to v. So therefore, t pi v is the same as tv. So we can replace t pi v in this equation with tv. All right. Small steps. And now we can take the norm of both sides and use the triangle inequality, right? Norms satisfy triangle inequality. So just take the norm everywhere. You still have equality. And then break up this into the sum of two parts, this part and this part, just using the triangle inequality. Okay. Finally, use that this is the maximum norm, and we know that t pi and t are gamma contractions. So therefore, this quantity here is upper bounded by gamma times the distance between v pi and v. And this quantity here is upper bounded by gamma times the distance between v and v star. Okay. So let's write it here. And we can pull out the gamma from both. All right. At this stage, we look here. We want to upper bound this. We are getting those terms, v pi minus v, v minus v star. We want to only see v minus v star. We are happy with that. That term on the right-hand side, we're happy about that because that's what we will, that's what we want to use to control the distance between v pi and v star. We're not happy with the other term, the v pi minus v. It's not a term that we want to see, but we want to see v pi minus v star. So we're going to subtract and add v star there and use the triangle inequality. So just for the first term is upper bounded by the sum of the distances between v pi and v star and v star and v. And we do this because then what we see is that we have this term, which is the same as this term, which is what we wanted to have. We have this term, which is disturbingly on the right-hand side, but it's multiplied by a value smaller than 1. Gamma is smaller than 1. So we will be able to move it to the other side and still get a reasonable inequality, right? So reordering this inequality, so moving just this term to this side, you get 1 minus gamma times v pi minus v star norm upper bounded by 2 gamma distance between v star and v. Okay. This stage, just divide by 1 minus gamma. Is this clear how I got this? I was reordering the previous inequality, right? Like subtracted from both sides gamma times v pi minus v star, which is a valid manipulation of an inequality. Then this disappears from the right-hand side. The minus gamma, this thing appears on the left-hand side, and that's why I have this minus gamma here. I had just this term was already there. And I put out 1 minus gamma. Okay? Okay, and so now I can just divide by 1 minus gamma, because lucky for us, we are assuming that gamma is smaller than 1. That's a positive quantity, 1 minus gamma. Therefore, if you divide both sides by this positive quantity, the inequality is going to stay correct. Right, and so this is the result that we were after. Two gamma over 1 minus gamma is the constant. That should have been here. All right. This clear? The very typical proof, there will be, there are many, many different results that one proves with some variation of this, like add and subtract, use that, these operators are contractions, reorder inequalities, and then you finally get the inequality you wanted to have. Okay. From here to there? From here to there? From here to here. Oh, it's just a triangle inequality. So here I'm subtracting from, in this term, inside, I'm subtracting V star and adding V star inside. And then breaking up that single term into two terms using the triangle inequality. Every step in the way, I'm like, is this a very ad hoc proof? Well, it's kind of like yes and no, maybe. I don't know. Like we wrote down what we know. We started to use what we know. Kind of the ordering does matter. It's again like playing chess a little bit. Like, oh, you have to make these moves, and then no, you checkmate in this order. Okay. All right, so what we conclude is that red, the blue, is at most 2 gamma divided by 1 minus gamma bigger than the red. That's how much inflation you can get. Is this real? Like, can you get that much inflation of the error? So you're, like, I call this the error because it's like Vn should be V star, but it's not quite V star, so that's kind of like an error. You're inflating the error a little bit. It turns out you can show that you can't, like, this is tight. Like, there are examples where you take a value function and it's close to V star, and then you take the greedy policy with respect to that, and no matter how close it was, the greedy policy gets this much factor further away from the optimal value function. So it's like, this is kind of real. Like, I call this a blow up of the error. Why is it a blow up of the error? It's because the 1 over 1 minus gamma, that quantity, 1 minus gamma is between 0 and 1. So 1 over 1 minus gamma is a quantity bigger than 1. The closer gamma is to 1, the closer 1 minus gamma is to 0, and the larger is 1 over 1 minus gamma. So if gamma is very close to 1, then you can expect a big explosion of, big blow up of the error. I'm going to use the notation that I'm going to denote by h1 over 1 minus gamma. And we often call this the effective horizon. In a way, you can argue that if you are in a discounted setting, in a discounted problem, by and large, this 1 over 1 minus gamma is characterizing how many steps forward you are looking into the future. You can make this precise, but it's not worth making it too precise. Somehow, it's a characteristic constant that describes how difficult, in general, problems with a given discount factor you can expect to be. And for gamma, main thing is gamma close to 1, this very quickly grows. And so with this, the blow up here is 2 gamma h v minus v star, just to practice writing things in terms of h. OK, so what I remember in general is that the blow up here is 2h, because gamma is smaller than 1. And so who cares? Like gamma is close to 1, then this is very close to 2h. OK. Any questions for this? Yeah.
So the operator is alpha Lipschitz, gamma Lipschitz, right?
Mm-hmm.
So I was wondering why I'm bringing this thing to the theorem. And the third part of the theorem,
Which was?
which was xn minus x star, the norm of that equals to half of the hand.
Right.
Essentially this, but
So-
instead of the 2
Mm-hmm.
gamma over 1 minus half gamma to n.
Right. So our theorem that you're talking about, that's the Banach fixed point theorem or the contraction mapping theorem. It guaranteed that this process of generating this V naught, like V1, V blah, 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 it has the property that Vn gets closer to V star at the geometric rate. This is great. This is good. We need this. But this is not enough. Because what we are doing here is something weird. We take Vn, we go to policy space, and then we come back. And that theorem was not talking about anything like that. Right? It's because we are not only interested in how well we are approximating the optimal value function, but we are also and mainly interested in how good the policy is that we are going to produce. Producing value functions was never the goal. It is just a tool. The goal was to produce good policies. Along the way, we're producing better and better value function estimates of V star. This is one way of getting better policies.
Just to clarify, so we can only use the theorem when we're mapping from the same space to the same time.
Yeah, that was a fixed point theorem, and fixed point theorems are talking about that you have an operator, and that operator is kind of like operating on the same space. Here you can take the greedy operator together with the policy evaluation operator. If you compose those two, then you have an operator that operates on the same space. Can we use that? Yeah. We will be able to use that. That's not quite what value iteration does. That kind of jumps forward. That's going to be policy iteration. So when you do this, like you're jumping there, jumping back, you made a move here in this space, and then you do the same thing. It's like greedy and then coming back. That's policy iteration. OK. All right. And that's actually the next thing to discuss. All right. But Okay, if we have any more questions for this, let me know. Maybe it's worthwhile to stop a little bit more. Yeah.
Is this book in the textbook?
It's in the notes. Yeah. I put up the notes, and in the latest notes, it's there. It's the dynamic programming. Oh, by the way, did you see the poem that ChatGPT wrote about dynamic programming? It's so beautiful. It's incredible. And ChatGPT was trained using reinforcement learning. Wow. It's a full circle. It should include into the poem that it was also trained by something related to dynamic programming. Next iteration. Okay. Anyways, next topic, policy iteration. By the way, just thinking very high level about what we're doing. Like, we have this MDP, and we are trying to get a good policy, right? And here we are assuming that you pretty much know everything about the MDP. You know the transition structure. You can read out the immediate reward function. You can read out this other function, the transition kind of for the states. And then you want to calculate a good policy. The size of the MDP is what? Like, it's how many states you have, how many actions you have. The data that goes into this calculation, how big the size of that is. It's basically, if you want to write a code, like, what's the input? Well, it's going to be the rewards, and it's going to be the transition probabilities for all state action pairs, the next state probabilities. So it's like the size of the tables that you need for the rewards is S by A, and for the transition kernel function, it's S squared A, right? Like, that's kind of the size of the problem in terms of S and A. And then normally, when we're in computer science, we want to design an algorithm to accomplish some goal. Like here, calculate a policy. We ask the question, how long does it take to calculate this policy, right? So we have everything in our hands. So this is kind of like an ad hoc procedure. Use value iteration, produce some stopping rule, and read out the greedy policy, and that's going to be a good policy. What is kind of missing is a stopping rule. Like, when do we stop this process, right? So if you want it to get, you decide ahead of time an epsilon optimal policy. How long, how many iterations of value iteration do we need to use to get there? But we have all the ingredients. So we know that Vn minus V star satisfies this inequality. And we know that if you read out the greedy policy, pi, which is greedy with respect to Vn, so this V is Vn, then you're only exploding the errors by this 2h factor. So if it's 2h, so before policy iteration, if 2h times gamma n is smaller than equal to epsilon, if n is so big, well, okay, there is one more factor. It's like V naught minus V star. If this is smaller than epsilon, then it follows that pi, which is greedy with respect to Vn, is epsilon optimal. V pi minus V star is going to be smaller than or equal to epsilon. Okay. How big is this? No idea, right? I mean, come on, we don't know V star, right? So that looks bad, like as if you couldn't use this, but actually you can. Because, well, okay, we make two choices. We can make the simplifying choice of Okay, the difficulty is V star. We can choose any V naught. Generally, this shows that if you can get a good guess about what V star is, for heaven's sake, start with the guess. Like that should be V naught. But if you have no idea, maybe start with 0. So we start with 0. So should work. And then you can show that star max norm is never larger than R max divided by 1 minus gamma. It's like the geometric series comes again. R max is the maximum value that you can get for the immediate rewards in absolute value. So this is h times R max. So it suffices if 2 times h times gamma n times h times R max is smaller than epsilon. From this, it follows that this holds. And from this, it follows that this holds, which is what we want. So now we can solve this for n. And if you solve it for n, you get gamma n should be smaller than equal to 2h epsilon divided by 2h squared R max. You take the log. You find that it's sufficient if this holds. You divide by log gamma. That's a negative number. Oops. OK, so the inequality is going to flip. Or you multiply everything by -1 first. Then you will have log 1 over gamma here. And here you will have log 2h squared R max over epsilon. And then divide. It's the same thing. So this is equivalent to that n is greater than or equal to log 2h squared R max over epsilon divided by log 1 over gamma. And then with a little calculation, and that's also in the notes, you can show that the 1 over log 1 over gamma can be upper bounded by 1 over 1 minus gamma, which is our magical age. So this 1 over log 1 over gamma looks complicated. You can just write h instead of it. You get an upper bound. Huh? So here you had n less than or equal to, but this was negative. And this is also negative. So I multiply with -1. The inequality flips. Then I can divide. That's why I also get log 1 over gamma and log like the reciprocal of this. OK. So log 2h squared R max over epsilon. OK. So this is how much effort is going to be needed by this procedure. So it scales linearly with h. So that's the number of iterations. Every iteration is going to cost you, I don't know, s squared a. So that's the total. Yes. Oh, OK. Yeah. So it suffices if, yeah. So we are writing if n is greater than or equal to this, then that implies that n is greater than or equal to that. So, yeah. Good. Yeah. Because we are taking the smallest integer, which is larger than the right-hand side. Because we're not going to choose an very large n. And so, and we can take an even bigger one. And this is an even bigger one, right? Like, take the smallest integer, which is larger than h times log 2h squared R max over epsilon. such an integer is going to satisfy that it's bigger than this quantity. And going backwards, then that's satisfied. That is going to result in a policy which is epsilon optimal. Okay. So this is the iteration complexity. Every iteration costs you s squared a. Okay, that's the total cost. H s squared a log something something over log 1 over epsilon. Because it's a log 1 over epsilon, this is like gets high precision fast. The logarithm function is very helpful there, right? Like if you want to double the precision, it's like you almost have to do nothing. It's like you add one more iteration, you double the precision. That's kind of the meaning. Okay. This was still value iteration. We didn't go to policy iteration. And like I have 4 minutes to cover policy iteration, which we'll not do, I guess. Although you know everything, so I could just say, yeah, do it. No. We're going to pay our dues to policy iteration next time. And we're going to compare policy iteration with value iteration and talk a little bit about like, okay, is this the best that you can do? Can you do something? All right, so here, one thing to note is that the MDP had s squared a parameters. Age was not a parameter, but the complexity depends on age. So this is kind of a non-uniform complexity bound. It's like just because the MDP has so many states and actions doesn't mean that you can get an optimal policy with value iteration regardless of the value of age. If age gets really large, this is going to take longer and longer time. You can actually show that value iteration does have this property. It cannot give you in polynomial time, just in S and A, an optimal policy. But if you fix age, you think about it as a constant, this problem parameter, it's okay. But it kind of tells us that like somehow this horizon does matter in these problems. Somehow like gamma getting close to 1 makes these problems more difficult computationally, or maybe, like we don't know yet, but like possibly, which is kind of interesting. It's like if you want to calculate shortest path in a graph, this is not what you get. Like it kind of, the cost, like the values that you're writing on the node, like the cost do not matter. You can get the shortest path. But here, it's not the case anymore. Okay. We finish early. It's okay. I took your time previously a couple of times. So see you on Friday.